Hi everyone, welcome back to Adrian's Digital Basement. For today's video, we're going to look at the Tandy 1000 EX and HX again. We're going to revisit this ridiculous RAM card that I made, this prototype, because something has come in the mail and it's a PCB that I designed to replace this. On top of that, I've received some new SRAM chips from DigiKey, so brand new ones. We can test out to see which of these work properly in my new board, but I'm getting ahead of myself. Let's get right to it. So first, let's take a look at the old board. Just want to address a couple things. People had mentioned on the comments in my last video that I needed to have bypass caps on these chips, and that might have been the problem why this thing wasn't working. As you can see, these are there. I haven't actually modified this board at all since the last video. These were installed right from the get-go. I reconfigured this board several times during all my testing, which explains a little bit about why these wires are kind of up like this. Originally, I had this board with the SRAM and one logic chip, and that wasn't working correctly, and I added a second one that still wasn't working correctly. I went back to this single chip, which, as you saw in the video, worked on the EX but not the HX, but all of that turned out to be the SRAM chip anyways, as far as I'm aware. Well, let's take a look at my new board that I've designed. So first off, I'm going to say this is the very first PCB I have ever designed in my entire life. This was a really interesting learning experience. I have no idea if this works. I haven't built this up yet. We're going to do that together on video. So if this board works, I'm going to put the KiCad files online and the Gerbers so anyone can download it and manufacture your own or modify it to your heart's content. So let's see if my first PCB ever is actually going to work. Now, one of the biggest issues right now is that the connection on the Tandys, which is these row of pins here, it's actually 2x31 pins, 62 pins total. That's a very unusual size. It's not really possible to find these types of things. Companies will manufacture the custom sizes for you. It's standard 2.54 millimeter spacing, so that's normal. But you're going to have to order large quantities if you're going to want to find the exact 62 pin connector. So what I found on AliExpress, and yes, I'm still ordering parts from AliExpress, this is a 2x30 or 60 pin connector, which if we just place this on here, now this is on the wrong side, but just an example, it leaves 2 extra pins. So to get the 2 extra pins, what I'm going to use is some of this single row stuff, and you just cut off the 2 pins you need, and then carefully cut down to as small as you can, which I've done on this one. And then it's a little bit jagged, so take some sandpaper like this and just rub it, which you can see I've done there, and you get relatively smooth part there. And I'm going to stick the extra 2 pins in just like that, and I think that should do the trick. That should work. For everything else on here is pretty much standard. We're going to put some sockets for the ICs here. So my last video, a lot of people had suggested that these marginal chips from China might have worked fine if I had used a bus driver. Well, in my design, just to be correct, I guess, I installed the 245 bus driver here. This is what connects the data lines on the SRAM into the data bus on the computer, which will help once you install multiple cards. And if you notice, I have 2 sets of pins here, which will allow this to go on the bottom, and then we can install a pin header on the top, which allows stacking of cards. Anyway, I'm going to build this up, and I'm going to speed up the video footage so you don't have to watch me do all the soldering. It's pretty self-explanatory stuff. Well, and just like that, the board is built up. Now I found I made some mistakes. First off, this jumper here on the left that says disable UMB, I take the jumper off, you'll see that the pins look a little different than this one right next to it. And that's because I accidentally used 2mm spacing for this jumper as opposed to 2.54. No big deal. I didn't have any pin headers around, but I used some leads that I cropped off the LED. And I happen to have some of the smaller jumpers. These came off an old hard drive or something like that. And they fit on there just perfect. Next mistake, see where it says disable UMB for this jumper that's too small? Well, that should read enable UMB. You got to put the jumper on there to enable the high memory. And what this one does, this jumper switches between 128K of high memory and I think 92K. Is it 92 or 96K? Whatever the intermediate is between 64 and 128. I think it's 96. What that does is, I actually wrote it on the bottom here. Upper memory is either 128K or 96, so it's 96, and it occupies C000 to DFFF or C8000 to DFFF. The reason why I did that is because the way the Tandy works is this 512K memory chip maps into the 0 to 384K, and it leaves 128K wasted. So I wanted to map it into the high memory, and you could actually load DOS and drivers and stuff into that space. The reason for the jumper to select more or less high memory is that if you're going to use an extra card, say the XT IDE, it needs room for the BIOS. Well, if all of that's taken up by the high memory, that's not going to work for you. You'll have to disable it entirely. And you would disable it by pulling this jumper off, and it would actually just free up that entire space. But if you set that other jumper, you will leave between C000 and C8000 free, which means you can map your option ROM. So that's why I included these. So in, of course, the revisions, I'll be fixing the pin spacing on this jumper, and I'll be fixing the writing that's on here, the silk screen, so it will be more accurate. Now let's look at what we have on this board. We have a bulk capacitor. This is just for the 5-volt power rail, just to help smooth things out. Of course, we have bypass caps for each run of the chips. We have an LS245. This is what connects the 8 data bus lines from the motherboard into the data bus lines on here. Next up, we have 2 logic chips here. We have an LS00 NAND gate here, and this is an LS32, which are OR gates. So these 2 chips are used to not only select this chip and also the 245 chip, basically turn it on so it writes and reads from the bus, but I'm also using these chips to also create a new address line 17. If it weren't for that, it would be overwriting some other RAM. It's kind of hard to explain. If you want more information on that, let me know in the comments and I can try to explain it. All right, we come to another one of my mistakes. These 3 resistors here, I put the pin spacing wrong on these as well. So if I turn the board sideways here, notice they're sort of up a little bit on one end, and that's because I just didn't leave enough space. That will be fixed on the next board revision. And finally, we have the LED. And you're like, what the heck is an LED doing on here? Well, I had an extra OR gate, and I decided to just put an LED, so when this RAM chip is being accessed, this LED will light up. RAM gets accessed very fast and a lot, so it's not likely this LED will ever be off entirely, but it will flicker and kind of get brighter and dimmer depending on what's going on with this chip. This is the connector here that goes onto the motherboard, and you see there's the 2 extra pins that I added. And then we have a pin header here, and this is so you can sandwich another board on top. Now, speaking of these connectors, you'll notice here there's a missing pin. Well, I made another mistake, and I noticed it while soldering this together. And let me get a new fresh PCB and I will show you what I did. So if you look right here, you'll notice there's a thick trace and it doesn't really seem to go anywhere. Well, this thick trace sort of just stops right there. So I looked at that and I was like, that's a bit weird. Like, what did I do there with that? Well, if we count from the top, 1, 2, 3, 4, 5, 6, 7, 8, 9. You'll notice this pin here has this large amount of copper under there. And what that is a flood fill. So see all this copper that's filled in on here? This is a ground plane. It's filling the entire space of the board. And that's what's happening right here, is because there were no traces going across, it just filled this in. But it goes from there over to that pin, and then this is ground fill as well. So it's all connected together. We start from the top 1, and we look at 9, because remember I had counted down 9 to get to right here where this ground fill is. Well, that's plus 12 volts DC. And unfortunately, it goes from the pin right there to the pin right there onto the ground plane. So if I connect this as is, it will short out the power supply, the 12 volts DC to ground. So that's not good. And what I did is I was able to just cut through the trace right there. It's very thin on that spot, which essentially broke the connection from this pin, which is what's connecting to the motherboard, right? The header is on this side on the right. So the 12 volts comes in here, fills through this area, but that's not connected to anything except right there. So I just cut through there. So that leaves this pin connected to ground. Well, that's not that big a deal because the board I'm gonna plug into the top connector. So this thing here, I don't use the 12 volts anyways, but just for good measure, I actually snipped that pin off. It will be hard to see, but I used an X-Acto blade and I cut through and I broke that connection. I noticed this after I had already connected this bottom connector. It's a mistake on my part. Luckily, all the other pins are absolutely correct. I don't know what I was thinking. I mean, I was referencing this was from the service manual, the technical manual for the Tandy. I didn't notice that problem. So at this point, we're good to go. Let's put this in the Tandy and try this out. So it opened the Tandys up. Remember the trap door, it slides that way. And if you try to slide it like this, nothing happens. But if you just push ever so lightly right there, it just slides very easily. There's a little bit of a lip there. This is inside my Tandy 1000EX. I don't have the RF shields anymore. You guys know what I think about those. I did write towards back on here. Not that you could put this in backwards. There's just no room in there. Actually, on this machine, you can put this in backwards. So if you do build one of these, just make sure you notice it says towards back there. So we just put this on, and because we have all 61 pins, you just get it on there and give it a push. So good old Commodore 1084, it's connected. I tested before plugging in the board that everything is working. It shows 256K, and let's turn this on. Whoa! That can't be good. Let me turn this off. Yeah, the problem I just had right there is I had this chip in there instead of the 245 that should have been on there. That's what you get for not paying attention. Here's a 245, and it happened to be sitting right there. There's the 245 installed back in the board. All right, let's give it a try. Uh-oh. That's not good. Power cycle this again. Yeah, that's so this not even, the computer's not initializing. I'm just gonna yank out the 245. This is definitely a 245 part here. HCT 245, in fact, fully TTL compatible. When I remove this chip, what that has the effect of doing is completely isolating the RAM chip from the data bus. So now the computer won't see the RAM chip at all, although the decoding logic is still going to try to decode the RAM chip as correct. Because this is not there, it's not going to be connecting anything to the computer. So when I turn this on, there we go, 256K. So computer's not damaged or anything, and it's not likely that it would be. And you can kind of see the LED blinking away there. I'm going to cover it with my hand. And that's because the decode logic, you know, it doesn't know that the RAM chip is not working. So anytime the system memory, which is now in the very low 0 to 256K, is being accessed as the computer boots, you see the light changing in intensity. So that's kind of neat. All right, well, anyways, I know this 245 chip is good. This is definitely a good one. It's brand new and it works in something else. So something is the matter with the way I wired this up. I'm going to have to do some troubleshooting. So I've done a ton of troubleshooting and I am not 100% sure what's going on. But what I did is originally on the prototype board, on this one, you see how there's 3 chip sockets. That's because originally I had wired this up in the exact same configuration with the same decoding logic as this board. And the only difference is I didn't have the LS245 on here. As you can see, there's no 4th socket. And this prototype board worked, and now this one's not working, well, at least with the 245 in there. So what I've done is I've installed jumper links in the socket to completely bypass the 245, and let's just see if this works now. All right, let's turn it on and see if it works. Okay, good sign. We have video. Oh, and look, 640K. So the boot disk that's in here right now is one I had configured while I was running the prototype board. And it has all the software on here to load DOS high. So if high memory is working properly, this will actually show it. So I'll speed this up. Sweet, well it worked. So what this does is it loads DOS into high memory, and you can see it's sort of showing the different addresses here. Now I have the jumper configured for the 96K, and you also configure it in the config sys. So it's loading DOS, or it's using the high memory from C8000 all the way through DFFFF. So if we type mem, we should see how much free memory we have, which should be a lot. 610K, which for Tandy is really good because remember, it only has 624K of conventional memory. It doesn't have full 640. It does, but the top little section of memory is used for a shadow of the video memory. Now what you can do is you can use the debug tool to see exactly where the memory is working and where it's not working. And case in point, if we look at DC888:0, this is the high memory and actually says DOS max right here. So remember, it starts at C8000, but I can change that jumper to make it map to the entire C000 all the way to DFFF. But if I look at DC000 right now, you see how it has dollar signs? This is what this Tandy shows anytime you try to access memory that isn't actually connected to anything. And here's an example. If I go to DB000, this is high memory as well, but I don't have anything mapped into there either, we get the same dollar signs. If we look at the C000 again, there it is. So what I'm going to do is I'm going to remove the jumper that disables that lower 64K of the upper memory, and when I do DC000, this will start working. So it's this jumper right here, it's the full size one that will convert between 128K and 96K. Now when we do the same DC000:0, we have random garbage. And this is expected, but the C is not showing dollar signs anymore because the RAM hasn't been initialized. It's just what happens when you turn on RAM. You end up with random garbage in it. In fact, I have something in ConfigSys called clearmem or something like that, and I specify clear the memory at boot up. It basically writes all zeros into this. So that jumper is absolutely being effective at enabling and disabling this memory. So I went ahead and I did all the troubleshooting just to check that the jumpers and the decoding logic is working. And I did that by booting up DOS without any memory managers at all. And I started looking with the debug program at the various blocks of memory, and everything is working properly, and these jumpers work fine. Pulling the other one off disables upper memory entirely, and then putting this one on makes it 96K, taking it off makes it 128K. So I'm really happy that works. So now the question is why doesn't it work when I have the LS245 in, yet why does it work when I have those jumper links in? Back when I was working on this board and I was testing those fake RAM chips, I did a lot of troubleshooting with my logic analyzer, and I still have those captures. So let's take a look at why I think the 245 is not working for me on this board. First, we're going to look at the data sheet of the 245. So you see 20 pins here, and there's a couple pins to note. There's the OE pin, which is output enable, and then there's the direction pin. The way I did it is on the right side here, I have data bus 0 through data bus 7 connected from the motherboard into this side of the chip. And then on the left side, we have, I'm going to call BD 0 through BD 7, and that's buffered data 0 to buffer data 7. This is what goes off to the SRAM chip. So the OE pin, this has the function of when it's high, that means that all of the data bus lines are high impedance, and I'm going to write high Z. It's the equivalent of them not being connected to anything at all. It's almost as if you took the chip out of the board completely. And when OE is held low, it actually connects the pins together. So I'm going to put con. So it basically will connect D0 to D7 through to BD0 to D7, or reverse. And that reverse is controlled by the direction pin right here. The direction pin, and if you look on the bottom of the sheet here, it says when direction pin is low, the D side is connected to the A side. So that's the direction. It would go this way. And when it's held high, it's A to B, so it's going this way. Now on my exact board here, I connected the direction pin to the MEM W pin, MEM right. And I connected the OE pin to the chip enable of the SRAM. So anytime that the DSLogic here, which uses address lines to detect whether the SRAM should be active or not, is telling the SRAM chip that it should be, it's also sending that CE or chip enable or output enable signal to this 245. And then the MW is asserted low by the computer when data is being written into the chip. So remember here it says low, B to A. So when the computer is trying to write to memory, and remember this is the computer side, so I'm going to put CPU, and this is the SRAM side, SRAM. When this is held low, this is going to go like this. It's It's going to go from the CPU to the SRAM, which is what we want. And anytime this is high, it's the other direction. It's basically as if the computer, the CPU, is reading from the SRAM. And here we go, high, it says A to B, A to B. Okay, so now we kind of get how this operates and how I hooked it up. Let's take a look at a logic analyzer diagram on this particular computer. Now this may not be super easy to see, and I'm sorry my inkjet printer clearly needs its heads cleaned. So here we have chip enable pin, and this signal is coming from my logic chips. Those two chips on the board that are selecting whether the SRAM and the 245 should be active. And remember, when it's low, which is like here, this is where it should be active. And then we have two more signals. We have MEMR and MEMW. So R is where the CPU is reading. So anytime you see it low, that means the CPU is reading from memory. But if you notice here, it's low, so it's reading from memory, but the chip select on the SRAM, that's a high signal right there. So that means that the computer is reading from some other place in memory and not the SRAM chip. So this is completely normal. And while MEMR is low, here's low, you see the MEMW signal for writing, which is the one right under it, is high. So you should never see these two low at the same time. That would be an illegal situation. Now when we look over here to this side, this is where the CPU is actually writing to the SRAM. So you see MR is low and chip select is low. MR is low, chip select is low. And I have lines here, and it's a little hard to see. The way the SRAM works is where the MR goes from low to high. So that's this transition right here. That's where it actually takes the data bus, whatever signal's on the data bus, it takes this and it writes it into memory based on whatever addresses are being selected. Now I don't show all the address lines, but all 18 address lines will tell the SRAM when this goes high, now write this memory into the SRAM. Okay, sorry there's a lot of explaining here going on, but this is all to basically describe what I think is going on. You see the chip select line? Now, it stays low the entire time, even though MEMW goes low, high, low, right? This is two different bytes of memory being written to the SRAM, but the entire time, the chip select line stays low. Part of the problem is when we look at this, chip select is currently keeping this chip active anytime chip select is low, and you see it stays low there, and you also see there's like these little bursts where it's low all throughout here. Now these bursts don't have any effect on the SRAM chip because the SRAM is only doing its thing when both the chip select is low and either MEMR or MEMW is low. And basically with these little bursts here, you see it's not. It's high and high and high and high. So the only time that matters is in these sections here, which is kind of like what I had over here with these lines. So here's where I think the problem is. So what's happening is when these little bursts of chip select happen here, and this is just due to address lines changing in multiplex address data bus lines on the 8088, it's causing the 245 to actually drive the data bus. Basically, it's putting a signal into the data bus when these little brief things are happening. And I don't think that should be happening. I made a fundamental flaw when I laid out this PCB. I should have reversed the connections, so put the CPU on this side and I put the SRAM on this side of the 245. And instead of using MW as a direction control, I should have used MEMR, the read one. And the reason why is because during these little brief selects here where chip select is low and MR would have been high, which is right there, actually it's what I had circled, then the only effect of what that would do on the 245 is it would actually drive the data lines that go into the SRAM chip. It wouldn't do anything on the CPU side. The CPU side would be left to whatever it's doing on its own at that exact moment. So I think what I'm going to do to test this is I'm going to remove these jumper wires and I'm going to put another socket in here and I'm going to manually rewire the socket so I can put the 245 upside down and I'm going to wire the MR signal into the direction control line. And that should allow me to see if this fixes the problem. So if that works, then all I need to do is go into KiCad and just fix the wiring on this to reverse it and then use the MR. And then unfortunately these PCBs that I have made will all be kind of crap and not very usable, I guess, unless I jumper it. Anyways, let's give this a test, see if this does the trick. Well, that's what I came up with. I put another socket, clipped off a couple pins, I reversed the chip and I soldered the pins that I want into the socket, and then I have run a couple bodge wires. Now the direction pin is this little bodge wire right here where there's a little dot there. So we're ready to test this out in the Tandy and see how it goes. Monitor's on, and this is the chip that when it was in before, we just had those green lines. 256K. Darn it. Oh boy. I had a bad connection here because this socket is only pushed halfway into there. That way the extra pins don't short. So I had to solder all the ones that are going through into the socket. And one of them was missing, one of the data lines. So yes, definitely not going to work without that in there. All right, let's try this one more time. Okay, 640K. Let's run check it, see if this is working. Well, you look at that. It's absolutely working properly. And let's check the memory map. Check out if the high memory is showing up correctly. It's currently set for 96K of high memory. And yep, there we go. So see, it says C000 to C800 is nothing. And then C8 to DFFF is available. Well, programs and available. Because that's I have DOS loaded right now. We pull this jumper off. When we run this again, we should see all 128K available now. So what it does is it's actually combining the Tandy's video RAM as high memory, but it's not really. So, which is why it's BC00 to C800. It's actually what's on the card is starting from C000 to C800. So this is now free because DOS hasn't taken it over with the memory manager. Now, people have theorized on my last video that if I was using an LS245 on my RAM board, that these marginal chips might have worked on the Tandy. I do have some actual chips from DigiKey, but the one we just saw running with Check-It was actually one of these marginal chips, although it was the one, this one right here, that always worked properly in the Tandy 1000EX, even with my homemade RAM board. These other ones, and the one that's on the board right now, all worked properly on the PC Junior and didn't work at all on this machine. And also, I didn't show this on video, but I did test one of these chips in this board when I had the LS245 bypassed, and it absolutely did exactly the same thing with those RAM errors as we saw on the last video. So the bird's nest wiring on this board wasn't the cause of these chips being marginal. Now that we have the buffer transceiver working on this machine, and this is actually an HCT245, which I personally think are a little bit better than the regular older LS type, let's see if the marginal chip that I just installed in here is actually going to work. And I'll be damned. It is actually working. So whoever theorized that a bus transceiver would actually make these chips work, you get a prize, because you were actually right. I'm going to quickly go through and test all of these chips on here and see if they're now working. To make it a little easier to show my testing, I created a spreadsheet matrix. On the left here we have the 5 China chips, which are these ones. And then we have 2 of the real chips. These are the ones I got from DigiKey. I only bothered testing 2 of them. Then we have the Tandy 1000HX, and we have 3 permutations: the handmade RAM board, the PCB, the new PCB, and the PCB with the 245 wired up, and the EX with the same 3 configurations. Now, right at a glance, you're going to be able to see what's going on. The 2 real chips that I tested from DigiKey, they worked in all of the RAM boards across both computers. On the HX, none of the China chips worked whatsoever in any of the combinations. But on the EX, very strange, is when I added the HCT245 and rewired it so it works, all of the China chips worked. But before doing that, remember I had one chip, this chip number 4, that was actually working. And it does work in the PCB and the handmade one. All of the other chips still show those same boot time errors on the EX, all these red boxes, and the same here on the HX. So I initially thought when I was testing on the EX that the 245 solved the problem of these marginal China chips working on the EX and would do the same on the HX, but as you can see, nope. And at boot time, those errors that we saw in the previous video are exactly the same. So some people commented that perhaps these China chips were working perfectly in the PC Junior because that machine runs at 4.77 megahertz, and these Tandys do run faster. And that is true. I think these run around 7.16 megahertz. But the weird thing is, that doesn't really explain the difference between the EX and the HX, is that both of these machines run at exactly the same speed. And to make all things equal, I actually have an NEC V20 installed in both machines, just in case the timing is slightly different between those processors. But even with that, you see the results right here, it's clear as day. So these China chips do work under certain circumstances, but they're certainly not reliable. So now onto this memory board. I actually had 10 PCBs made up. Luckily, because of China, it's not very expensive to do this. Well, unfortunately, due to my design errors on these, I'd say that these aren't really worth using. And yes, of course, it's easy enough just to jumper the 245 and bypass it. And then with those other minor fixes I mentioned earlier in the video, these are working PCBs. But after this video, I know what to do to fix these, so I'm going to fix the schematics and I'm going to upload them along with the Gerber files to GitHub for anyone to access. So check in the link in the description below if you'd like to look at how I did this. So with that, you're free to download the KiCad files to modify this stuff to your heart's content, or you can just download the Gerber files and use JLPCB or PCBWare or whoever your favorite PCB manufacturer is to make your own Tandy RAM expansion boards. Now, if you're interested in getting one of these particular boards, the ones with the problems, for yourself, drop me a line at the email address on my channel about page, and I'll gladly send one of these to you just for the price of postage. Well, that's going to be it for this video. I hope you enjoyed this and the previous two parts on my endeavor to make a RAM board. The China chips really threw me for a loop, and I've learned an invaluable lesson with that. And designing and making a PCB for myself has been absolutely fascinating and so interesting. I'm going to be definitely making more in the future. So keep watching to see my endeavors making more of these things. If you haven't already subscribed, please go ahead and do that. Hit the little bell button if you want to be notified when I do post videos. Please put your comments and suggestions down in the comment section below. And thank you very much for watching. Goodbye.